Now, so far with sine, cosine, and tangent, what we've done is we've been able to find the value of sine, cosine, and tangent. We didn't so much do tangent, but if I wanted to find, say, tangent of 45 degrees, we could be able to find it by plugging it into the calculator, and it would give us a value. And tangent of 45 would be, I think it's, yeah, because we can type tangent of 45 into the calculator, and we can get a value, because we did the same thing with sine and cosine. Tangent of 45 degrees is 1. So we can actually plug these into the calculator and get an answer for sine, cosine, and tangent. We've also used sine, cosine, and tangent to solve for missing sides, because we know that sine of a given angle is equal to the opposite side length over the hypotenuse. Cosine of a given angle is adjacent over the hypotenuse. And tangent, opposite over adjacent. Sine is opposite over the hypotenuse. Cosine is adjacent over the hypotenuse. And tangent's opposite over adjacent. And we've been able to use these to solve for missing side lengths. Now, the last thing we can actually solve for is angles. If we're given the side lengths, we can actually solve for the angles. But the issue with this is getting the angle out of sine, cosine, or tangent. So we need a way to get the angle out. And what we can use is something called inverses. Because sine of an angle will give us the ratio of sides. So the inverse of it would give us back to the angle, or should anyways. So let's look at these here. So we can type these in a calculator. Now to get sine inverse, we're going to go second sine. And then we can say sine of 47. 74? Yep. $74, and we get 74. So second sine 74. Now we can also do the same thing for cosine inverse, because we can say second cosine inverse of cosine of 21.5. 21.5. And the last one we have tangent inverse. A tangent of, I think it's 58, is what we have. And if we do this here, we get 58. It will not. Because there are some restrictions for how this works. Now, sine of an angle is equal to our side lengths. We'll call it y here. We'll call this x. Because we can plug in any angle, technically. Because any angle that we want, positive or negative, we can plug into sine, cosine, and tangent. But as we saw when we first looked at this, the graphs of sine and cosine, they had a maximum and minimum at 1. We couldn't go greater than 1, and it actually can't go less than negative 1. So the y values here are restricted between negative 1 and 1. Now for the inverse, sine inverse, we end up taking y is equal to x. So we're switching the values of x and y, which means the values that go into this here for the side lengths, because we're talking about side lengths inside for sine inverse, cannot be greater than 1 or less than -1. If they go outside of that bounds, I can't actually take the inverse of it. So there are some restrictions on what we can use sine inverse and sine, and it does get a little bit more tricky when we get out of the range for what's inside here. When for sine, it's between -90 and 90 degrees, and for cosine, this works very well if we're between 0 and 180. It's kind of just based off the functions. We don't get too far into this because for us, the main angles that we're focused on are in a right triangle, so either one of these angles here won't be greater than 90. So for sine, cosine, and tangent, we don't come into any issues for that there. But in the trigonometry class where we actually look at stuff beyond 90, there's a little more technicality we have to focus in on with inverses, with sine and cosine and tangent. But for us, this works out fine. Because if tangent of A is equal to x, then tangent of inverse of x is equal to the angle. And you don't have to write all these in, but the main thing I would kind of emphasize is if we have sine of A, if I take sine inverse of both sides, we get the angle by itself. If we have cosine of A and I take cosine inverse of both sides, we can get the angle by itself. And the same thing is true for tangent. So now that entire core concept is located straight in the book. So if you look at 9.6 and wanted to get that down, it is straight out of the textbook. But I think this here is more important than just being able to copy that down, is actually understanding what we're doing. So here, guys, we're saying the tangent of A is equal to 0.79. So the ratio of the side lengths for this tangent value is 0.79. Now to get the angle by itself, well, as we just saw, I can take tangent inverse. And as the example problems that we saw, tangent inverse of tangent of A is going to give us what? A. Because the tangent inverse and tangent for this here will cancel each other out. But what I do to one side, I have to do to the... So on the other side, we're taking tangent inverse of 0.79. So in this here, we can go second tangent inverse of 0.79 and hit enter. Huh? And we should get 38.3. Did y'all get the same thing? So this here is telling us that the angle is 38.3 degrees. And that's it. If I want to find the angle, I'm really taking tangent inverse of both sides, for if it is tangent, to find the angle. Okay. So for the second one here, we have sine of B is equal to 0.87. So what are we going to do? So we're going to apply sine inverse to both sides. Yes. Let me go back. So 79 is what I plugged in when we needed 75. 36.86. Yep. Let's fix that. Go 75. 75. 36.86 exactly 36.9. Yep, so that was just a copy error. Thank you for catching that. So that does change the value by almost 2 degrees. Okay, so yes. Any other questions on the first one besides that copy error? Okay, so we do have the second one correct here because we are using 0.87. And if we type this into the calculator, sine inverse of 0.87, we would get So for this last one here, what would we need to do? So here we have cosine of c is equal to 0.15. So what are we going to use? So we're going to apply cosine inverse to the other, both sides, because we're taking the inverse of both functions. Cosine inverse of cosine of c is just going to be c is equal to cosine inverse of 0.1 is what? 81.4. Now that might seem odd for this one here because the angle for cosine, that's pretty big, yes? And we know what? The biggest side is opposite the biggest angle, smallest side is opposite the smallest angle, and the middle side would be in the middle. Well, for this triangle, we know one of the angles is going to be 90. For us to be able to do this, we're looking at a right triangle, which means the other angle has to be small. Actually, it would be 8.6 degrees. But this here is dealing with what? The adjacent over the... So the side that's actually opposite this angle would actually not be the hypotenuse. Actually, let's draw a triangle out. Because it would be this angle right here, yes? Which makes this the longer side, but we're still talking about the side next to it. The 1.5 is actually not talking about the side opposite the 81 degrees. It's talking about the side opposite the 8.6. Because if we draw the triangle, let's actually do that. Draw it nice and big. Angle, as we found 81.4 degrees, yes? Well, cosine is what over what? Adjacent over the... So the relationship of these two sides is the 0.15, which means whatever this side length is would give us a value bigger than 0.15, because that side should be the bigger side. Does that kind of make sense? I mean, it's not hugely important for this here, but it is kind of nice when we're looking at this here. Sine of 60 degrees, okay, we do have a bigger number, because that 60 degrees is actually the side opposite. It's dealing with the opposite. There's a connection between these. But if it's kind of hard to see, it's not that hugely important, but it's kind of interesting to note that these relationships with sides and angles still holds true throughout all of them. Any questions on this here? Okay. So for the first one here, what are we going to do to both sides? We're going to take which one? Inverse of tangent. Tangent inverse of our 3.29. And tangent inverse of 3.29 is? 73.1. Now what would we do for the second one? Sine inverse of 0.55. And lastly, to find C, we're going to take cosine inverse of 0.87. Questions on this here? Okay. Do we feel comfortable with kind of finding these angles, given the ratio of the sides? Do we need to see another example of these three here? Okay. Solve for the right triangle, round decimal answers to the nearest tenth. So, how many things are we finding? Because we do know the value of angle C. It's 90 degrees. Do we know the other two angles? Do I know all three sides? So, I'm solving for the value of C and for angles A and B. Now, looking at this here, well, C is probably going to be the one that's easiest to solve for first, because we actually don't need to use sine, cosine, or tangent to find it. What can we use? Pythagorean Theorem. A squared plus b squared is equal to c squared. So, A, B, and C, which ones do we know? Which are? And 2 squared. So 2 squared plus 6 squared is equal to c squared. Well, the 2 squared and 3 squared are on the same side of the equation, yes? So I could type that whole thing in. Because I could type in the calculator 2 squared plus 3 squared. And if we did that or did it individually, well, 2 squared is 4, 3 squared is 9, and 4 plus 9 is 13. And last but not least, what do we need to do? Square root both sides. So C is equal to the square root of 13. Any questions on this so far? Now, we need to find the values of A and B. I'm going to erase this here so I have a little more room. Now, A and B are angles, yes? So if I wanted to use, say, sine, could I use that for angle A? Because what would sine of A be? So sine of A is opposite, which would be over the hypotenuse, which is the square root of 13. So could I use sine to find this? Well, that's one of the setups we kind of had already. Could we use cosine to find angle A? Because it'd be the adjacent side over the hypotenuse, yes? Could I use tangent of angle A to find the measure of angle A? Because opposite over adjacent, yes? Because for any of these here, for sine I need opposite and hypotenuse. Well, we have those. For cosine I need adjacent and hypotenuse. We have those. And we also have opposite and adjacent because I do have all three sides, yes? So let's see what we get. If I wanted to solve for sine, or for angle A using sine, at this point we would do what to both sides? Sine inverse. Take sine inverse of both sides. And here the sine inverse and sine would simplify each other out, leaving us with inverse of sine of 3 divided by the square root of 13. And again, we can pull up the calculator and say second sine inverse of 3 over second square root of 13. Which gives us 56.3, and it goes on out, but we'll keep it to the nearest tenth, which tells us that this here is 56.3 degrees. Okay. Let's look at cosine of A. Well, again, we're going to do a similar method, except instead of taking sine inverse, we're going to take cosine inverse of both sides, which these will cancel, telling us A is equal to cosine inverse of 2 over the square root of 13. A is equal to 56.3 degrees. And if we use tangent, well, applying tangent inverse to both sides would get these two cancel, telling us A is equal to tangent inverse of 3 halves. And A is so if I have all three sides, does it matter which one we use? No. But if we weren't asked to find all three sides, it would tell us what we need to do, because we would need to see which side lengths are given. But realistically, if we find the third side first, we can find either angle. We can pick which one we want. And that's why I'm using this here to kind of show you all that. Now, we found that A is 56.3 degrees, yes? We still need to find the other angle, yes? How can we do that? Huh? Triangle's not 360. So we know that this is 90, yes? Well, we can add those together. 90 plus 56.3. And if we add these two together, well, we'll have the 0.3, 146. And we can subtract 146 from what? 180. So angle B would be 33.7 degrees. Now, questions on this here? Let's do it the other way. Let's say I'm just going to pick tangent. Out of all three, I'm just picking one. Tangent of B. Well, the opposite side length of angle B is 2, and the adjacent side would be. And if we apply tangent inverse to both sides, we would get that B is equal to tangent inverse of 2/3. So second tangent inverse of 2/3 33.69, which would round to 33 point. And that works too. So really, looking at this here, and they might want you to approximate the square root of 13 to the nearest tenth. But for the angles, I would leave it as the square root of 13. Because square root of 13 will give us a more precise answer for the angles. Because if we round the square root of 13, which means our approximation for the angles is going to be off by that rounding. But looking at all this here, how much of these did we actually have to use sine, cosine, and tangent for? Well, square root of 13, we used Pythagorean Theorem, and then just found one angle. And used the fact that the sum of the interior angles is 180. So let's look at this next one here. Pythagorean Theorem. A squared plus b squared is equal to c squared. Now they tell us the values of a and b are 20 and 21. So we can say 20 squared plus 21 squared is equal to c squared. And 20 squared plus 21 squared, type that in, because 20 squared is 400. 21 squared would be 441, which gives us a total of 841. But we can't leave it there. We have to find square root of it. Point, or is it 29 flat? No. That's very nice. So we see that the hypotenuse is 29. And as we saw in the last one, we don't need to really find both angles. I just need to find one, because if I have one, I can find the other. Okay. Now, do we want to use sine, cosine, or tangent? Does it really matter? No. So we'll say tangent of E is equal to what over what? So the opposite side to angle E is 20, and the adjacent side is 21. Now to solve for the angle, we have to use our inverse, tangent inverse. And the tangent inverse and tangent will simplify out, leaving us E is equal to tangent inverse of 20 over 21. So E is 43.6 degrees. We can add them together and subtract from 180, but we know that one of the angles is what? 90, yes? So the other two have to add together to be 90. So to find our other angle, we can take 46.3, and subtract it from 90. So the measure of angle E is 43.6. The measure of angle D is 46.4. And the hypotenuse was 29. Questions on this here? Let's look at another one. So this one here is a little bit different because it did not give us the two sides. It gave us one of the sides in the hypotenuse. So we're still going to use the Pythagorean theorem. A squared plus b squared is equal to c squared. Now this time we know we can say a is 1 plus b squared is equal to 109 squared. Well, we can't just plug it all into the calculator. $8,281 plus b squared is equal to 109 squared is 11,000. So we do have to, we don't necessarily have to, but we can square both of those there and then do what, guys? 8,281 from both sides to get b squared by itself. And get b squared as so let's see if y'all can do this without a calculator. So what's the square root of 36? So 36 times what is 3,600? Would be 36 times 100, yes? What's the square root of 36? The square root of 100. So 3,600 would be, because we would do 6 times 10, which is 60. And you can plug it in the calculator and see if we got the right answer. So that tells us the other side length is 60. So looking at this here, do we want to find h or g first? It doesn't matter, so we can find g first. Yeah. So we'll say cosine of angle g is equal to the adjacent side over the hypotenuse. The adjacent side would be, and the hypotenuse is 109. Now at this point here we would use cosine inverse and apply it to both sides, because cosine inverse and cosine will simplify out, leaving us with angle G is equal to cosine inverse of 60 over 109, which tells us that the measure of angle G is 56.6 degrees. Now we still need to find the measure of angle H. Because the two acute angles add together to be 90. And that's it. Questions on any of this here? Any questions on anything we've done today? Do we need to see another example of one of these? No. Well, before we officially end it, does anybody have a guess at what that side length is for AB? Is not that site. 7. Or Pythagorean triples. Yeah. It is 3 whole numbers that plugged into the Pythagorean theorem give us a true statement. So it's saying that 7 squared plus 24 squared is equal to 25 squared. So if we looked at a calculator, 25 squared is 625. 7 squared plus 24 squared is 625. So having a few of these, or kind of recognizing a few of these, is helpful. 3, 4, 5 is one of the most popular ones, or any iteration of it. So multiplying them by 2. Pythagorean triples. Yeah. Yeah, we can still use Pythagorean theorem, because Pythagorean theorem would say that we have a squared plus 24 squared is equal to 25 squared. We can subtract the 24 squared from both sides. Now we can't, those will cancel because they are the same. But is 25 and 24 the same thing? No, they're 2 different numbers, yes? So we would have 25 squared minus 24 squared. 25 squared minus 24 squared gives us 49. Second square root of 49 gives us 7. And that's all we're doing for today.